Okay, this is bonding, lesson 2, and tonight we're going to talk about the difference between the two major categories of compounds: ionic compounds, in which electrons are transferred, and molecular compounds, which electrons are shared. I want to make sure that you know that molecular and covalent are synonymous when we're talking about these types of compounds. So if it says which of the following is a molecular compound, you're looking for something that's covalent, which means that it's made up of all nonmetals. So make sure that you can use those words interchangeably. Let's get started. Metals are pure substances found to the left of the staircase. We already know that because we just did the periodic table unit. And atoms of a metal do not bond with other metal atoms. Metals share a sea of mobile valence electrons. This allows metals to conduct current. And this is also called wave energy. And we're going to look at a little video of metallic bonds. And I like to refer to this as the big dog theory. So what's happening here, if you see these dogs, okay, they each have a bone, and the bones are constantly moving. So what we're going to, how we're going to relate this to metallic bonds is the dogs are like copper atoms. So if I had a bunch of copper atoms, the electrons just constantly move back and forth between the copper atoms, and those bones represent the electrons constantly moving. So if I had a bunch of Cu atoms, and this was kind of like the dogs, the electrons are constantly moving in between the atoms, and it's these mobile electrons that conduct current. Ionic versus covalent. So let's look at ionic bonding. Ionic bonding is between a metal and a nonmetal. And this is called the big dog theory, because basically the bigger dog, meaning the one with the higher electronegativity, is going to steal the little dog's bones or electrons. So you've got big dog versus little dog, and the big dog steals the bones based on its electronegativity, and it steals the bones from the little dog. Well, this is like ionic bonding, because chlorine has a higher electronegativity value than sodium. So chlorine is going to steal sodium's electrons. Notice how each dog had a bone, and when the little dog got near the big dog, they got into a little tussle there, and the big dog wound up with the bones. And now the little dog is trying to be friends with the big dog because he wants what he's got. Now we're going to look at covalent, nonpolar, and covalent polar. And then we'll take some notes. So let me briefly explain the difference. First of all, covalent means that electrons are shared, as opposed to in an ionic bond where electrons are transferred. Nonpolar basically means no pull. And what that means is one of two things. It means that I'm dealing with Brinkelhoff, because if I have a diatomic element, for example, Br2, there's a zero electronegativity difference. If I look up the electronegativity of bromine and I subtract them, electronegativity. So there's a zero electronegativity difference. That means that I'm nonpolar. There's no pull. Let me show you an example of this. We've got Br with 7 valence electrons. And then another Br comes in right next to it, and it's got 7. So now this Br's got 2, 4, 6, 8, because they're sharing these two in the middle, and this bromine's got 2, 4, 6, 8. They're sharing those in the middle, and everybody's happy. So there's no pull here because the charge is equally distributed. They're sharing equally. Now, another way I can be nonpolar is if I'm nonpolar by symmetry. And what that means is, let's look at the molecule CH4. Carbon's got 4 valence electrons. 1, 2, 3, 4. And then we have an H come in over here with 1, an H come in over here with 1, an H here, and an H here. H is happy because H only wants 2. So each H has got 2, and carbon's got 2, 4, 6, 8, so carbon's happy. This is what's called non-polar by symmetry. And what that means is the pull is equal and opposite. If we were to look at just a CH bond, the carbon would have a higher electronegativity than the H. So technically, it would be pulling the electrons in. So if this is my C, it would be pulling this way in all 4 directions. Well, if I'm pulling in, this is equal and opposite. They cancel out. If I'm pulling down and up, this is equal and opposite. So the charge distribution, or the pull, is equally distributed. So this is considered nonpolar by symmetry. So let's look at what that looks like according to our big dog theory. So here you have 2 chlorines, and they each have a bone. They get into a tussle, and because they have the same strength or electronegativity, they're going to share the bones equally. And that's what happens in a nonpolar bond. In a nonpolar bond, there is no pull. In other words, there is an equal charge distribution. Now, let's look at polar. Polar means that there is pull. One element has a higher electronegativity than the other. So if I gave you an example of HCl, and we were to look up the electronegativity, you would see that Cl is higher. So we say that there is pull in this direction. Now, what that means is you basically create a dipole moment, and I'll explain this more in class. So because chlorine has a higher electronegativity, it's actually going to pull these electrons closer to chlorine. So this side of the molecule gets a slightly negative charge, and this side gets a slightly positive charge, and those are the symbols that we use. And this is what's called a dipole moment. The arrow is always in the direction of the element with the more negative charge. And we put a cross on the tail, which looks like a plus sign, which means that this side is slightly positively charged. So let's look at what this looks like. So you can see that the big dog, the fluorine, the one with the higher electronegativity, is taking more of the bone than the little dog. You can see how the big dog's got more of the bone in its mouth and the little dog's only on the end. So this is the same with electrons. The element with the higher electronegativity is going to pull the electrons slightly more toward its side, which gives it a negative charge, leaving the... This is ionic compounds. Electrons are transferred. Sorry about that. So in this case, we have sodium wanting to give up one, chlorine wanting to gain one. And when that happens, the element that is gaining electrons, I'm going to redraw it over here. The element that's gaining electrons gets brackets around it. So when Na loses an electron, it forms a positive ion. And then chlorine gains that electron, there it is, and when it does that, we put brackets around it, and it now has a -1 charge. So this is how we would draw the diagram of an ionic compound. The nonmetal gets the brackets. Both elements have a charge. Na lost one, chlorine gained one. Now this is positive, this is negative. Now they are attracted to one another and they'll form a bond. In general, ionic compounds have high melting and boiling points due to strong bonds. They're considered electrolytes, meaning they conduct electricity in solution, and they're usually very hard. Here, chlorine is 3.2, sodium's 0.9, electronegativity difference is 2.3. Remember, the greater the difference, the greater the ionic character. All right. So let's review. In a covalent bond, electrons are shared. And here we're looking at water. So you've got 2 H's and oxygen needs 2. So one of these is going to come in here and one's going to come in here. And what that looks like when we're all said and done is you've got X, H, X, H. And that's how you would draw the diagram. Oxygen's happy it's got 8, and each H is happy it's got 2. Now these links don't work. That's why I showed you the other links. Let's look at some physical properties of covalent compounds. They have low melting and boiling points due to weak intermolecular forces. IMFs means intermolecular forces. Okay, so let's see what this word means. When we talk about roads, we have an interstate, which is a road that goes between states. And then we have an intrastate, which means within the state. So inter means between. So if this is intermolecular forces, it is forces between molecules. So that's what that is interpreted as, forces between molecules. Okay? It is a non-electrolyte, which means it does not conduct electric current in solution, and it's usually soft. So now we have to make some changes here. When this was created, it was using the old reference tables. As of 2011, some of the elements have changed their electronegativity values. So this is 3.4 for oxygen, and these are 2.2. So to find the difference, you take 3.4 oxygen, we only use one H, minus 2.2, and that gives us a difference of 1.2. So this is a polar molecule. This is a polar molecule. There is an unequal charge distribution. Oxygen, 3.4, is going to be pulling up on these electrons that it's sharing. So the oxygen side of the molecule is going to be slightly negative, and the hydrogen side of the molecule is going to be slightly positive. So the dipole moment is in the oxygen direction. The greater the electronegativity difference, between two elements, the greater the percent ionic character. The closer the electronegativity difference, the greater the percent covalent character. Electronegativity scale goes from 0 to 4. We can classify a compound as ionic or covalent in two ways. Look at the elements in the compound. A metal and a nonmetal equals ionic. Two nonmetals is covalent. The greater the electronegativity difference between the elements, the greater the ionic character. The closer the electronegativity difference between the elements, the greater the covalent character. You have to determine the electronegativity difference and then determine whether the compounds are ionic or covalent. So we need to go to table S and look at electronegativity. And we know that H is 2.2 and oxygen is 3.4. This is the one I showed you earlier, so it's going to be 3.4 minus 2.2, which gives me 1.2, and this is covalent. Next one, two nonmetals. Generally speaking, if you're less than 1.7, you are covalent, but there are some exceptions. So here we've got Ca, which is a metal, and it's got electronegativity of 1, and oxygen, which is 3.4. So 3.4 minus 1 equals 2.4. So this is greater than 1.7. It's definitely ionic, but plus we can see that it's a metal and a nonmetal. NaCl, this is 0.9, and Cl is 3.2. So you've got 3.2 minus 0.9, which is going to give you 2.3, and that's definitely ionic. Metal and nonmetal. FeCl3, iron 3 chloride, and iron is 1.8 and chlorine is 3.2. So this is going to be a difference of 1.4. Now, this is considered ionic because it is a metal and a nonmetal, but this electronegativity difference is less than 1.7, so it's ionic with covalent character. H2O2, so we've got 2.2 and O is 3.4, so it's going to be just like water, 1.2 covalent, and then diphosphorus hexoxide. Phosphorus is 2.2, oxygen is 3.4, so it's the same, 1.2, and that's covalent. And 3 more. Oops, 2 more. I already did that one. LiH. Li is 1, H is 2.2, which is 1.2. Again, this is less than 1.7, but this is a metal and a nonmetal. So this again is also going to be ionic with covalent character. And CH4, carbon is 2.6, H is 2.2. So that's going to give us 0.4, and this is covalent. Okay, that's it for tonight's lesson.